All right. So let's flip the page and do some more problems. Give you guys some more practice when it comes to it. So give fair warning. This is actually a very, very difficult question. It's not that hard. It's just a very conceptual question. It's pretty crazy when it comes to it. It was more theory than actual applications of it itself. Okay. So crazy example. It says, let's find the volume of the pyramid whose height is h and the base is an equilateral triangle with sides A. Now, if you're wondering what in the world is going on here, so let's see. So essentially, let's suppose we have, this is the y-axis, right, and this is the x-axis here. Okay, right, this is our x-axis. Okay. And let's suppose we have one pyramid, right? So everybody knows what a pyramid looks like, right? But our base is an equilateral triangle. So it's a triangle base and a triangle going up. If you kind of think of it that way. So it kind of looks like this, like that. It's a triangle within a triangle. So the best way to graph this is just try to make a equilateral triangle centered at the x-axis, and here's our origin, and just make lines going out to there, to the points. That's kind of what's happening here. So each side length is length A, and this is our height of the triangle, right, when it comes to it. Right, so the height's right in the middle when it comes to it. So essentially, if I make a slice, right, so if I just make a slice like we usually do here, what we end up getting is just a big triangle. So this is the x-axis, this is the y-axis. Where this is the height, right, from the point to point. And this is the length of side A. Now remember, to find these volumes is essentially we're taking the integral of the areas. So we know the area of a triangle is 1/2 base times height. And we already know the height is given to us to be h, so that's good. But the question is, what's the base value, when it comes to it? So what's the area of, what's the base value itself, right? And h depends on how far we go. Like, for example, if I make our triangle here, okay, what's that base and what's that height associated with it, right? So it's a little tricky when it comes involved with that kind of stuff. But the good thing is we kind of know how to do this. It's been a while. You probably haven't seen it in this while. But we're going to use similar triangles that help ourselves out. Okay. So again, we know the entire length is h. We know this is base A. So I'm going to call this side, this little triangle here, has a base side of B, and the height is going to be x. Whatever the x value rocks it on the x-axis. So if we associate similar triangles, so we know that the height of the small one is associated with the height of the big one, and this same ratio is equal to the base of the small one to the base of the big triangle. And now we just solve for b. So pretty straightforward, just multiply that side. So b is equal to ax over h. Okay, and now we can find the area of our rectangle, area of our triangle. So this is going to be the volume now of 0 to h, because we're going, that's our height we're going to go to, right? We don't know exactly what it is. It could be like 1,000, right? And whatever the h value represents, of our area, so 1/2 the base, which is ax over h, times the height, which is now in this case just x itself, dx. I told you it's kind of crazy example. You can do very, very much theoretical stuff when it comes to this kind of stuff. But again, right, the whole process is just getting there. So once you get there, it's actually not that bad of an integration to deal with, right? So, for example, we could bring this to the one outside, and then we just have ax squared over h dx. And notice a and h's are constants. So x is only the only variable we're taking the integral of, which is, kind of nice. So if that's go away, essentially is what's the integral of x squared? Well, that's x to the third over 3, and just add everything else on top of it. And there you go. Yeah. And again, right, everything else, you plug in 0, it goes away, so 0 doesn't go with it. We're just going to plug in h and 1/2 into it. So that's just going to be a h to the third over 6h. And notice these simplify. So our answer is a h squared over 6. So that's actually the volume of this pyramid. So even theoretical stuff we can actually apply. It doesn't always have to be numbers, which is, pretty cool stuff, right? So you can find the volumes of pretty much anything as long as you have the functions you can create based off that information. Okay. Right. So a couple more, again, just to give you guys more practice when it comes to it. Okay. So this one says, find the volume of the solid that is obtained by rotating the curves y equals 6 minus x squared and y equals 2 about the x-axis. Okay. So again, let's just draw it and see what's going on. So we know y equals 2, so it's not going to go past this line, that's for sure. So let's just graph this. Okay. All right, so plug in 0, we get 6, right? So that's way up here. That's not good. Plug in, let's say, 2. I plug in 2, that's 4. 6 minus 4 is 2. So plug in 2, I get out 2. So it crosses there. And if I plug in 3, so x equals 3, I get 6 minus 9 is negative 3. Right? Yep. So if I plug in 3, I get negative 3. So it's kind of looking like this. It just goes down that way. But remember, we just care about the rotation of y equals, so this line here where it crosses here. And we're rotating about the x-axis, so this portion right there when it comes to it. So if I rotate this, and again, remember, it's a parabola, so it actually goes in the opposite direction as well. So we know 2 works, so if I plug in negative 2 down over here, I also get 2 out here. If I plug in negative 3, I also get negative 3 out. So it's going looking like this. Okay. So if I rotate this way, so in other words, this whole thing is being rotated down this way, like that. You guys see that? So if we rotate this way, so now we have, again, you don't always have to use the Washer method if you don't have to, right? We can use the Dix method if we, the best thing is we know we can use the Dix method, right? That's the best part, using that Dix method when it comes to it. And that's what we're going to do. We're actually going to be using the Dix method because, again, notice when we rotate this, there's no gaps within it, right? It's just like a solid line going this way, a circular motion when it comes to it. Okay. However, we can't use the Dix method going this way because, our radius is not from here to here, right? Just a constant line. It's actually from here to here. It's changing. You guys see that? So that's going to be going from here to there. That's going to be our disk going here. So we're going to rotate this way.